right, we're about to get started here. So the way it's gonna work, similar to last times, if you watched it or you're here for the last one, I'm just gonna go through the entire practice exam, and then we're gonna take questions at the end of the practice exam. All right, so I'm just gonna get started with this first question right here. Gonna bring over the iPad screen. Just 1 second. All right, so we're supposing 10% of people who get tested have breast cancer. So I'm going to start with 100 people, so that way we can represent it as a percentage of the people in the population. We know that 10% of those people are going to have cancer, and then the 90 don't. If someone has cancer, the test will give a positive result 60% of the time. So we know that 6 of the 10 are going to be positive, and the remaining 4 are negative. And if they don't have cancer, it'll correctly give them a negative result 90% of the time. So it'll correctly give them a negative result. For the 90 people that we have, 81 of them will be marked negative, and then 9 will be marked positive. So if somebody tests positive, what is the probability they do not have cancer? So we can just take our 9 people who are marked positive out of our 15 total people with cancer, and I get that by just adding the 2 positive tests together, and we should get 9 out of 15 is a correct answer. Does anybody have any questions on how I did that one? Just a reminder, you do have to have a YouTube account in order to chat. All right, well, if there's no questions on that, I'm going to move on. But if you do have a question on that, I can go back and answer that. All right, and so this one is asking how to convert code into a real-world example. So we have red, green, and blue. And we know it's not going to be the cards or the die. So it's obviously like the best choice here. All right, if we have wheels with wedges numbered 1 through 8, what is the probability both wheels land on the value 8? So I'm just going to draw this out because the wheel problems can be a little bit tricky. It always makes sense to draw them out. So we have 8 different options for each wheel, and if we're looking for both wheels to land on 8, that only happens once, and then there's 64 other opportunities or 64 total opportunities, so it's going to be 1 over 64. If you have any questions, just throw them in the chat. We can answer them, but I'm going to go ahead and go on to the next one. So we have a study conducted on 96 people or freshmen at a university on whether or not they drink coffee. We're drawing 5 students without replacement. What is the probability that at least one student is a coffee drinker? Well, this is the probability rule, that probability of at least 1 is equal to 1 minus the probability that none of them drink coffee. So we're just going to calculate the probability that none of them drink coffee and then do 1 minus that. So if we're drawing 5 students without replacement, the probability that the first student is not a coffee drinker is 35 over 96. And the probability that the second student is 34 over 95, since we're not replacing the students we already drew. So we can keep going down to 33 over 94. And then 32 over 93, and we're drawing 5 students, so it's 31 over 92. And so then we can just kind of plug this into our Prairie Learn, and then we'll just subtract that from 1. So we'll do 1 minus 34 over 96, or 35 over 96, times 34 over 95, times 33 over 94, times 31 over 92. All right, let's just check that. 35 over 96, 34 over 95, 33 over 94, 32 over 93, and 31 over 92. That looks good to me. I can have Angela explain Bayes' rule in chat, and then if you need more explanation, I can do that a little bit later too. All right, so now if Wade buys a lottery ticket every day with a probability of winning of 0.025, the probability that he wins for the first time on the third day, we can just take the probability that he loses on the first 2 days, which is going to be 1 minus 0.025 squared. So that's the probability that he loses on those first 2 days, and then we'll just multiply that by the probability he wins on the third day of 0.025. So since it's a multiplication, the order doesn't matter, so I'm just going to go this way, 1 minus, and then square it. And that's how we do that question. All right, so there are 12 birth months, and assume that the probability of getting each birth month is equally likely. In a group of 5 random people, what is the probability that there is at least one birth month match? It's a good question. Yeah. So if we have 12 birth months, each person's going to have a random one, and we're looking for the probability that they match, and we're looking for at least one match. So again, this is P of at least 1 is equal to 1 minus probability of none. So the probability of no birth month matches is going to be, so we'll start with a room full of one person. So we'll go 12 over 12, because that's a probability that in a group of 1 that there's a birth month match, times 11 over 12 times 10, at least I think it's this. And then we can just do the 1 minus again. It's been a while since I've answered this question, so if I get this one wrong, I will explain this one better. I just need to check my work here. Yeah. So yeah, it's again, P of at least 1 is equal to 1 minus P of none. So this is the probability that in a room of 1 people, there's no birth month matches, or so we can kind of just ignore this one. But in a room of 2 people, we just multiply 12 over 12 times 11 over 12 because those first 2 people don't share, times 10 because there's going to be the first 3 people don't share, times 9 of the first 4 people, and 8 of the first 5 people. So that's probably none of them do. We subtract that from 1 to get the probability there's at least one match. I know I kind of rushed that one, so if you need me to explain that one again in more detail, I can. All right, so this is I think this is applicable for the Bayes rule thing here. So if we have, what is the probability that somebody who's 55 years old will reach the age of 60? So probability of 60 given 55 in this case is going to be equal to P of 60 divided by P of 55, because it's the probability of this can also be represented as P of 60 and 55 because once they're 60, we know they've already reached 55, so we're just going to represent it as P of 60. And then divided by the probability that they are 55. So it's going to be 0.859 over 0.907. And that should give us that probability. 0.907. And then for this question, the probability of a man who just turned 70 will die within the next 5 years is 0.165. What is the probability that the man will live for the next 5 years? So if we know that he will live for the next 5 years, we just have to take the probability of living, which is 1 minus the probability of dying. So 1 minus 0.165. And then we just have to multiply that by the probability that they are 70. So times 0.669. Any questions on how this question works? All right, I don't have anything yet, but I will go on to the next one, and I can go back at any point. All right, below is a survey about student handedness and gender. If we select a student randomly from the male students, what is the probability that the student is ambidextrous? It's just going to be the number of ambidextrous males over the total number of males. 349 and 7. All right, so this question is about a deck of cards. So there's 52 cards with 4 suits and 13 for each card. Or 13 cards for each suit. I don't think I've done the juror question. I did a similar one to the juror question. It's a similar methodology that I use. It's the cancer question. It was like the first or second question I did. So if you need to look at the juror question, if I don't get that one, I'll do it again. But I did a similar approach as to how I did the cancer question from problem 1. Why I do 1 minus is it should be in your notebook, but a law of probability that if we're looking for at least one to occur, it's going to be the same as 1 minus nothing occurring. Because if nothing occurs, then we know that nothing occurs, and probabilities have to add up to 1. So if we want 1 or more, it's just going to be 1 minus the probability that nothing occurs. Does that make sense? All right, in the meantime, we'll go ahead and answer this question. We're drawing 2 cards at random with replacement. What is the probability that both cards are not kings? Okay, so if we know that there are 4 kings in a deck of cards, we can do 52 minus 4 to get the total number of cards that aren't kings, and that's going to be 48 over our total number of cards, which is 52. And then we can just go ahead and square that because we're doing it because we are drawing 2 cards and we're replacing the cards, so the probability won't change. So it's 48 over 52 squared. Cool. Okay, so I'm going to go ahead and finish this one, and then I'll go and do the juror question because I think there's a chance I'll get it still, so I don't want to go ahead and do it now to get it again later. So what is the chance of getting either all tails or no tails on 5 losses? So we're looking for the probability of all tails, or the probability of no tails. And since it's a coin, it's a 50-50 chance either way. These are going to be the same 2 probabilities. But I will, so we just have to do the probability of all tails. It's probably the first one is a tail times the second one times the third one times the fourth one times the fifth one, or 1/2 to to the 5th power to get 1 over 32 for all tails. And then probability of no tails is the same thing because this probability of heads is equal to the probability of all tails. So we can just do 1 over 32 plus 1 over 32 to get our answer of 1 over 16. Does anybody have any questions on how this one works? All right, no questions. I'll keep on going. So if we draw 2 students randomly, what is the probability that none are female? And we're replacing them so the probability won't change. So this is what's the probability of drawing 2 males. So it's 315 over 696 squared. And that's how we go ahead and do that one. It's similar to this deck of cards question we did earlier. The logic behind the 2 problems are the same. All right, this one is a fun question. So it's asking for, on a day with a certain weather forecast, what is the probability that he gets Papa John's for dinner? So all we have to do for this one is we have to take the probability of each weather condition times the probability he gets Papa John's on that weather condition. So we're going to start by doing the probability he gets Papa John's when it's sunny, on a sunny day, or on a day where it's 70% sunny, 0.70 times 0.28. And then we'll do the same thing for rainy, 0.2 times 0.35. And then for snow, or for cloudy, 0.10 times 0.37. 0.7 times 0.28 plus 0.2 times 0.35, 0.1 times 0.37. I know this question can be tricky because it's just a lot of like words, so if you need me to go back and re-explain that, I can, but I'm just going to go ahead and go on to the next one, unless there's any immediate questions. All right, so we're spinning 2 wheels labeled 1 through 8 because let me space this out more. So 1, 2, 3, 4. And then same way going down. What is the probability that both wheels land on the same value or wheel 1 has a value greater than 7? So I'm going to call horizontal wheel 1 and vertical wheel 2. So first, let's calculate the probability that they both land on the same value. So 1, 1, 2, 2, 3, 4, 5, 6, 7, 8. So we get 8 over 64 plus, now we have to go ahead and do the first value is greater than or equal to 7. So I'm going to go ahead and do this one in a different color. We'll go purple. So now we'll just go wheel 1, so we'll go across and mark off all of the ones where it's greater than or equal to 7. I'm going to go 1, 2, 3. So we have 16 over 64. And then with the addition rule, we know that the addition rule is going to be P of A, which is our 8 over 64, plus P of B minus P of A and B. So we just have to subtract the overlap here. And I am getting overlap at where wheel 1 is 7 and where wheel 1 is 8. So we'll just go ahead and subtract off 2 over 64. 4, what's that going to be? 22 over 64, it looks like. Sometimes I suck with adding right off the bat. Yeah, it's 22 over 64. Any questions on that one? Because this one is a tricky wheel addition rule problem. I get confused on it sometimes too. I'm going to go ahead and take a few seconds, wait for questions if there are any. All right. I'm going to go ahead and move on to the next question. I think there might be a little bit of a delay, so I am able to go back if needed. All right. Wheels labeled 1 through 5. What is the probability it lands on a multiple of 3? So, and 1, 2, 3, 4, 5. There's only one number that is a multiple of 3, and that's going to be 3. So the answer is going to be 1 over 5, because there's one success over 5 attempts. All right, so we are looking to draw a female out of all of the left-handed students. So there are 30 left-handed females and 89 total left-handed people. So we can just divide those two numbers together. All right, we got one more question on the prediction and probability, and then we'll go on to the simulations and distributions hereafter. All right, we're taking an exam with 5 true-false questions. So probability of correct on true-false is 1/2. If you guess randomly on each question, what is the probability that at least one question has an answer of true? So if we are guessing true on all of our questions, we have a probability of success of 1/2 on each question. So we can just go ahead and calculate we know the probability of at least 1 is equal to 1 minus the probability of none. We've done that a few times now. So we'll do probability of, so now we have to calculate the probability that they're all false, so we get them all correctly. So it's going to be equal to 1/2 times 1/2 times 1/2 times 1/2 to give us 1 over 32. And we'll do 1 minus 1 over 32 for our answer. I think this question might be worded a little bit weirdly, because if you guess randomly on each question, what is the probability that at least one question has the answer of true? I'm thinking it's that you get at least one question right. So I'm just going to go ahead and calculate 1 minus probability of getting none of them right. And yeah, so that's how that works. Let me go ahead and zoom in a little bit too. Now that we're doing some coding. All right, so we are writing a simulation, and the first step in any simulation is to create an empty list. And so now we have our empty list, and we called it data. We're going to go ahead and do our simulation 5,000 times. So it's going to be a for loop. So we're going to do each round 5,000 times. I can go over that one right now. Since that's on the first part. I'll finish this one and then I'll go over that juror question, so that way you can get your answer and figure that out. So we need to create wheel 1 and wheel 2, and they're going to be random numbers between 1 and 10. So now that we have our wheel 1 and our wheel 2, I created them just by using that random.ranInt function. You should have used that a bunch in this class. And then now we have to do the dictionary part, so we call that D. We're going to set D equal to wheel 1 and then it's colon wheel 1, and then wheel 2, colon wheel 2. And we're going to add that to our list. And then pd dot data frame of data. So what we did is created our data list, did a for loop of 5,000 times because that's what the question asked for. Wheel 1 is a random integer between 1 and 10, same with wheel 2. And we add those to a dictionary, which is always going to be the syntax of a string for the column name, and then what you want to add to the column, and then string of comma, string of column name, what you want to add to the column. And those are separated by colons. And then we're going to do data.append d to add it to our list. And then we can do pd.dataframe, capital D, capital F of data, and that'll make our data frame. All right, cool. We got that one. All right, I'm going to go ahead and try to find the juror question on one of these practice exams. All right, cool. Wait, I have to go ahead and pull that up again. All right. Why is it not here? Here we go. All right, so suppose jurors make the right decisions about guilt and innocence 50% of the time, and that 80% of all defendants are truly guilty. So we're going to start with this second line of 80% of all defendants being... Yeah, I can go ahead and go over that too. 80% of all defendants are truly guilty. So we'll start with our 100 people again. We know that 80% of them, so 80, are guilty. And 20 are innocent. And that of those, each respective ones, the jurors are correct 50% of the time. So we know 50% of 80, so 40 people are convicted, and 40 are acquitted. Those are the fancy ways of saying found guilty and found innocent. And we're going to do the same thing over here. So 10 guilty and 10 acquitted. Oh, I'm using the Bayes rule? Yeah. Well, so what I always try and find to do on the exams is to do it the easiest way possible. So I would always recommend doing this tree version, because you do have a paper and a calculator, and on when you take the exam, so you can do it. If the tree doesn't work for you, you can also do it the table way. But yeah, I guess I can. Yeah, I'll do that. I'll finish this way. So that way people who don't want to use Bayes rule can do this, and then I'll also try it the Bayes rule way. So we're looking for the chance of an innocent defendant being acquitted. So we have 10 innocents out of 20 total people. So it's a 50% chance. So for the tree version, what you want to do is you want to get it down to this leaf level of, you just kind of work your way down. So we get 40 convicted, and then you just kind of add up what you're looking for out of the total number. So if it's like, of all of the acquitted people, how many are innocent, or like what's the probability of an acquitted person being innocent? It'll be like 10 over 50, because we have 50 total people acquitted and only 10 of them were actually innocent. But in this case, what is the chance of an innocent defendant being acquitted? It's just going to be our number of acquitted over a number of innocent, so 10 over 20, which is also 50%, which is given in the question. But I can go ahead and try this more ways too. So yeah, can I get that last one back or no? Okay, cool. All right, and then we can try this the Bayes rule way. So if we know that we need to find the probability of acquitted and given that they're innocent, we need to find the probability that they're acquitted. So probability of acquitted given innocent. I'm just going to show you how that they both work out to the same way. So first we need to calculate the probability that someone's innocent. Is going to be equal to 0.8 or 1 minus 0.8, so 0.2, because we know that 80% of all defendants are truly guilty. And then the probability that they're acquitted given that they're innocent is going to be equal to, we know that the jurors are right 50% of the time. So probability of acquitted and innocent is going to be equal to 0.2 times the probability the jury is right, so 0.5. And that gives us 0.1. And the probability of acquitted given innocent is probability of acquitted and inno over probability that they're innocent. So we can do 0.1 over 0.2 to give us the 0.5 again. And then the table is just the same way as the tree. You can just kind of make it into a table. And you have guilty and innocent. Sorry, we'll go this way. Guilty and innocent, and then acquitted, convicted, and total. We'll do 100 people again. And so we know that 80 of them are guilty, 20 of them are innocent. And then we know that it's 50% of the time they're right. So we'll go 40 and 40 because we're just multiplying 0.5 times 80 for each one. But if it was like 0.6, you would do 0.6 times 80 for convicted and guilty, and then 0.4 times 80 for acquitted and guilty. And then same thing, we're looking for acquitted and innocent divided by the total number of innocents to give us that 0.5 again. So do any of those ways like work for you best? And did any of them make sense? Probably. Yeah, in this case we can, because it's just like 50%. But you're not always. I would always recommend working it out because, like, if I hit new variant here, it's gonna ask for like a different thing. Or I guess in this case it's not. But yeah, here's one where they're wrong, but it's still the same number, but like it's gonna be different every time. But yeah, you can I guess you can think of it that way, but I would always just recommend working it out because you never know what you're gonna get on the exam. All right. But do you understand like how you can work that out to get the answer no matter what the probability is? Or do you need me to go through like one more here? All right, I'm gonna go ahead and move on to that spinning wheel with the. I did. You can kind of rearrange it a little bit, but I did the P of A, and P of acquitted given innocent is equal to probability of acquitted and innocent over the probability of innocent. Yeah. So do you want me to go over using the formula, or do you want me to go over with like a table or a tree or whatever you think was best? Formula. Okay. So for this question, it's kind of the opposite of what we just did. So we're looking for an innocent person given that they're acquitted. So the probability that, so first we need to work our way and get the probability that someone's acquitted. And so for a guilty party, it's going to be 0.7 times 0.2 because it's the probability somebody's guilty and that the jury is wrong. So that's going to be like 0.14, I think. And the probability that somebody's innocent and acquitted is going to be 0.3 times 0.2, so 0.06. Or sorry, 0.3 times 0.8. Because it's the probability they're innocent times the probability that the jury's correct. And then innocent given acquitted is gonna be I personally resort to the tree method whenever I get a little confused because this can be tricky. So it's 80, so it's 80-20 again, and then we know that it's 70-30, so 0.14 or 14 and whatever that is. And then we know it's 24. So it's just going to be our innocent and acquitted. I hope I'm over our total probability that they're. We can just add these two together because if you think of that in terms of the tree, it's just acquitted and acquitted. Sum that up, so we get our 24 over. Please. Oh no, that's wrong. What did I do wrong here? Oh. 1 minus. Yeah, that's why I always try and use the tree, just because it's very easy to make a mistake. But in this case, we had to do 1 minus on that. I think I flipped a number here or there. So sorry if that got a little bit confusing, but yeah, it's. Yeah. All right, I'm going to go ahead and go on to that spinning wheel problem. Yeah, the juror question's always a little bit tricky, so it does make sense to always just work that through in multiple different ways. So we're spinning 2 wheels, 1 through 9. And again, we've got wheel 1, wheel 2. What is the probability that both wheels land on even values and the first value is less than or equal to 5? So let's first start off with, I'll do this in orange. We're going to start off with the probability that both wheels land on even values. So we got 2 and 2, 2 and 4, or 6 and 2, 8 and 2, 2 and 4, or 4 and 4, 6 and 4, 8 and 4, 2 and 6, 4 and 6, 6 and 6, 8 and 6, 2 and 8, 4 and 8, 6 and 8, 8 and 8. And then I just want to make sure I didn't miss anything. Okay, so we've got 4 rows of 4, so we have 16 even numbers, or where they're both even, over 81 options. And then now we have to do, we're doing and. So now we have to figure out where the first value is less than or equal to 5 and it's both. So now I'm going to mark in blue where the first value is less than or equal to 5. I just did lines because it's just going to go all the way across. And so now each of these are 9, and there's 5 of them. So we're going to have 45 over 81 values be less than or equal to 5. And since it's and, all we want to do is just count where they overlap. So we've got all of these ones have it, so it's both. Both of them are even, and it's less than or equal to 5 on that first value. Or sorry, I went the wrong way. Whoopsies. The first value is this way. It's going to be the same thing, but, just for continuity. Again, it's going to be 45 over 81, and then there's only 8 overlaps. So 8 of the 81 are both less than 5, and both of them are even. Yeah, you can use the multiplication method, but with the wheel problems, again, these ones are always tricky. I always draw them out. Yeah, so, well, we can think of the probability that they're less than 5 for the first value. It's the first wheel has to be less than or equal to 5, so it's going to be 5 of them, and the second wheel can be any of the 9, so it's going to be 45 over a total combination. So that's how we're calculating this. You can do this by hand without drawing it out, and then think of the second one. It's where they're both even. There's not going to be a lot of them. And so you can, where they're both even, there's 4 for 2, because there's each of them have 4 different ones, or 4 different even numbers. So that's where we can get that 16 from, is just by multiplying those two together. That's why I always try and draw these out, because you can use the formula, but the formula, if you don't know what you're doing, will usually give you a mistake. And then so I just usually like to just count them out. So yeah, if you get tripped up by the formula, there's almost always a way to draw it out. with the jury question, with the wheel question, with the dice question. So now I'm going to go ahead and go into the code questions, and if there's any more of those, any more questions we'll do at the end of the code questions when we finish this. Just that way we can segue into the coding questions. Okay, so we're trying to coordinate a photo shoot for an RSO. 75% they arrive in orange, 25% they arrive in a blue shirt. So first we need to write a function that has one parameter with a default value of 100. No, it won't take you too long. I think if you practice the 50-minute version, once you get 100 on the untimed, if you can do that and get a grade you're happy with while drawing it out, you shouldn't run out of time if you can draw it out quickly. So like I've done these a bunch, so like that's why I'm able to draw them out quickly. So I think if you practice drawing them out, it won't take you too long. I personally drew them out when I took it, and I did not run out of time. I was still able to finish on time. And if you can get the coding questions done quicker as well, you'll also save yourself some time, give yourself more time to draw it out. So if you're better at coding, I would just speed run all of these coding questions. And then if you're worse at like the drawing it out, you have more time to draw it out. But if you're better at drawing it out or better doing the formulas quickly and worse at coding, do those first. Because it's nice, because if you look at the assessment, it's divided into the two sections. So here are your coding questions, here are your probability questions. So there's always a strategy in how you play things. But yeah, so this one, we're already given our function with our default value, and we just have to run a simulation. So let's start by doing that. So again, data. First step always is data. Second step is the for loop of count. We don't want to do 100 because if we did 100, we wouldn't be, if they changed the value of count when they called the function, it wouldn't use their value, it would use 100. So we want to use count instead of hard coding it. And then we need to create a shirt variable. And we're going to use the random.choice because we want to use orange or blue instead of numbers. And so we're going to do a list of 3 orange to 1 blue, because if you do that, that is 3 oranges out of 4 total shirts, which is 75%, and 1 blue, which is 25%, which is exactly what we're looking for. So that's how we get the shirt, and then we can just do our dictionary, shirt, colon, shirt, data.append d, and then we can create our data frame anywhere we want. Yeah. So it all depends on the strategy you use is how you can finish quickly. So instead of saving it, I'm just going to return pd.dataframe of data. Or you could do this and just df is equal to this, and then you can return df. Either of those two ways work. Yeah, we got that one right, so let's go ahead and move on to this next one. Probably the simulation is of spinning 2 wheels labeled 1 through 14. Each wheel is stored as a row under the columns wheel 1 and wheel 2. Find the probability you get at least one value less than 6, and the second value is greater than 10. So now if we think about it, there's no possible way for wheel 2 to be both less than 6 and greater than 10. Oh, yeah, so 2 ways. You can return df is equal to pd.dataframe. You can save the data frame and then return it. Or, since you don't have to do anything to the data frame, you can just return this part of the code right here. So if I go to here, you can get rid of this line and just return this line. Both of these are valid ways of working. Let's go next. So yeah, so it's impossible for wheel 2 to be less than 6 and greater than 10. So in this case, we don't have to worry about, since it's an and, we don't have to worry about when the second one is less than 6. So we can just do, we'll create a df of successes, and then we'll just do df at df dot wheel 1 is less than 6, and we have to wrap this in parentheses because we're doing multiple conditionals, and wheel df dot wheel 2 is greater than 10. And now just to show you why it won't work if you why the statement that wheel 2 can't be both less than 6 and greater than 10 is important. We'll just we'll code it in to show you why it doesn't work, and then oh wait, actually, nope, there's gonna be an error because I forgot to wrap these in the parentheses. There we go. Oh, I guess that works. But you don't need this wheel 2 is less than 6. Both of these ways work because wheel 2 can't really be both less than, yeah. They do both work, but if it gets confusing, you don't need it. Yeah, if there's an or statement, so I'm going to draw it out. But if you hit shift and then the button above enter, so shift and the button above enter is or, and then shift 7 is and. So that's how you can code the or statement instead of the and statement. All right. But yeah, so if sometimes it's confusing, you can just try and find ways to eliminate some redundancies if you're struggling. All right, the current simulation so we need to add 4 questions. So we'll just go here and go 3 and 4, and then we'll go ahead and copy this, and we'll change it to 3, 3, 4, 4, and yeah, this one we just gotta manipulate what they already gave to us. All right, to get the sample space of possible results, in this case it's talking about the numbers, not the colors. So we can just go 10 times 6 times 20, and that's the total number of combinations of numbers we can get. Cool, so we have to calculate the probability of exactly 1 red marble and 1 white marble. So there's 2 ways of getting 1 red and 1 white. The 2 ways are red, then white, and then white, and then red. So we have to calculate both of these ways. So again, we'll start by creating our df success. And that's going to be equal to df at where df dot draw 1 is less than or equal to 4, because that'll give us red. It's going to be 2 conditionals, so and df dot draw 2 is greater than or equal to 9. Or, and then we have a second set of conditionals. We'll do df dot draw 1 greater than equal to 9, or df dot draw df dot this is in the way, draw 2 is less than or equal to 4. So those are going to be all of our successful outcomes. So we can just do length of df success divided by the length of df. Probably a typo somewhere. What? That should be right. I don't know why that. Oh, this needs to be an and. There we go. Sorry about that. Yeah. So, like I said, there were two outcomes where red and then white and then red. So we'll separate each of those into its own parentheses. So this is the first draw is a red, the second draw is a white, or the other outcome is this draw is a white and then this draw is a red. This one is the same as this question, so we just have to multiply all of our numbers together to get that many possible combinations. Alright, so we're going to write our random season function. So for that syntax is def random season, and then we don't need any parameters. It's just going to randomly choose a season. So that's the random.choice function again. And it's winter, spring, summer, fall, and then we just return season. Yeah, so that's the end of the practice exam. Took us about an hour to complete it, and that so I'll open the floor to any questions that didn't get answered so far. So if you have any questions, I'll go ahead and answer them. So yeah, I don't have any more questions to answer. I'll hang around for a little bit longer if there's questions from the floor. But if not, you guys can, this stream should be uploaded shortly after we end it here. Yeah, of course. Any questions? Any questions? Yeah, so doing the tree method, let me go ahead and pull up another jury problem. Alright, so tree method on a jury problem. Gonna try and get a good one here too. Let's go ahead and make this full, actually. Bring over this one. Alright, so jurors are correct 90% of the time. So jurors are correct 90% of the time, and 85% truly guilty. Sorry about the chicken scratch up top. All right, so I'm gonna go ahead and hopefully make this bigger. Make it a little bit easier to see. So we'll start with our 100 people. 85 guilty, 15 not guilty. And then 90% of the 85 is 0.9 times 85. 76.5 are convicted. And then the remaining 85 times 0.1, 8.5 are acquitted. And then we got to do the same thing over here. 15 times 0.9 is 13.5. And 15 times the 0.1 is 1. You can do 1.5 or you can do it however you want. Acquitted and convicted. So that's how we get that. I'm going to go ahead and get the iPad out of here real quick. What is the chance of an acquitted, so somebody found not guilty, being actually guilty? So we're looking for acquitted. So of our people who are acquitted, we have 13.5 plus 8.5. So that's 22 people. There's 22 total people acquitted. Of those 22 people, what is the chance that somebody's acquitted and they're actually guilty? 8.5 of that 22 came from the guilty side, so we can just do 8.5 over 22. And then that's how that works. That make sense? For the tree method question? Of course. All right, so I'm going to go ahead and get that wheel question up real quick. All right, and it's a coding wheel question. Is it this one? All right. So, is this the kind of question you guys are looking for? Where it says, you find an estimate of the probability that you get at least one value less than 6, or the second value is greater than 10. I think there's a slight delay. I'm going to wait for you guys to answer. Yeah, okay, cool. So, we have a simulation stored in data frame. So first, let's create our DF success. And our DF of success is defined when we get one value less than 6, or the second value is greater than 10. So we'll start with subsetting our data frame. So we know that it's going to be X or Y, right? So let's start by figuring out what our X is. So our X is you get at least one value less than 6. Let's just go ahead and get at least one value less than 6. So DF'd out, we get DF'd out wheel 1 is less than 6, or our DF'd out wheel 2 is less than 6. So there's our X condition. That'll give us either A or B, either X or Y. And then for our second condition, it's going to be or the same value is greater than 10. So that'll give us this condition. So it'll be either wheel 1 or wheel 2 is less than 6, or wheel 2 is greater than 10. I had the arrow the wrong way. Or wheel 2 is greater than 10. And the probability is defined as the number of successes over the total number of attempts. So our total number of attempts is going to be DF, and our number of successes is going to be the length of our data frame of successes. Yeah, okay, yeah. Got it correct. Let me know if that way makes sense to you guys. It's a coding question, so if you needed the non-coding version of it, I can try and find one of those, but I don't know if there are any. For the two that had this question, does that make sense? Yeah, Jack, this is going to be posted after. I already did the Illini t-shirt question. I can go over my code again if that works for you. If not, I can do it from scratch. Do you want me to do it from scratch, or do you want me to just go over it? Going over it? All right, yeah. All right, so I think this part is just what's given to you. This and then the return value. No, it's no problem. It'll take me like a minute or two. And there's no other questions right now. So this is the function header. We got the function name and the parameter of count. It has a default value. So if somebody were to pass in a value, they could pass in whatever value they wanted to. I can do the sum of dice problem too. If they don't put anything in, it'll just default to 100. And so this is a simulation, so we're going to start with our data list. So we always create an empty list called data whenever we want to make a simulation. And then we're going to do a for loop in range of the number of people that they're expecting. So we're just going to use count, because if it changes from 100, we want our code to change from 100 too. And then we're going to figure out, we're going to randomly choose a shirt. So we know it's 75% chance of there being an orange shirt, 25% of there being a blue shirt. So we do 3 oranges to 1 blue, because a 3-to-1 ratio gives a 75 to 25% chance. Then we throw it in the dictionary, append it to the list, and then create a data frame and return it. Most of this stuff is just standard simulation. I'm guessing what you got hung up on was how to randomly choose 75% of an orange shirt. But let me know if it's something else that you don't understand. Oopsies. Joshua, does the question make sense now? Awesome. All right. Let me go ahead and get some dice. All right. So we've got our sum dice function. So we need to create a function called sum dice that takes the variable dice as a function parameter. So that's the first thing we're going to do. So def to create a function, sum dice is the name of the function, and it's going to have a parameter of dice. So this is how we create a function every time. Sometimes you don't need a parameter, but in this case we do, so we're going to have one. Alright, now what do we want to do? The value of dice will tell us how many dice to roll, and it should have a default of 2. Alright, so we're going to default the dice to 2. It's very similar, or it's exactly similar to this count equals 100 from the orange shirt question. The sum dice function must return the sum of rolling dice, 6-sided dice. So if we know we want a sum, and it's going to be a rolling sum, so it's going to count the number of times, or it's going to count the sum for each dice roll. We need to create a sum variable. We're going to set that equal to 0 because we haven't rolled the dice yet, so we have 0. Our sum is 0 because we haven't rolled anything. Now we're going to start rolling our die. So we're going to go for I in range dice. That's going to give us a for loop that will, we're going to try and add the number we rolled to our rolling sum. So sum is going to be equal to random dot rand int 1 to 6. So that's going to be our new roll plus what we already had on our sum. So we're going to add our current sum. So if we roll a 5, we currently have 0, so our sum is going to be 5. And then the next time through, we're rolling 2 dice. We have a second dice to roll. Our sum is 5. We're going to roll a 3. Our sum is going to be 8. And then so on. And then until we reach our number of die. Or dice. Whatever the plural is. And then we're going to return sum. So that's how you go ahead and do that problem. Does this code make sense? Of course. Any other last minute questions? Because this is not a simulation. This is just a regular for loop. We're not trying to store this into a data frame. We're just trying to find the sum. So I guess another way to do this is you could do this way. You could create a simulation and then return the sum for the column. So I'm just running the simulation real quick. Create a data frame, and each one's going to be a roll. You do right about here. So you do return when that's what your final answer is going to be. You return it when you want that to be your final answer. So in this case, we want our sum to be equal to df dot at a roll column dot sum, and then we're just going to return the sum because that's what we want to return. If we wanted to return the whole data frame, we would just do return df. Oh wait, why is that not working? Oh, well, in this case they don't want you to do a simulation, but you could import just import pandas and do it this way. But it's way easier to do it that first way. They both work though. I would just do it this way. And then in this case, you want to do return df here because the df's been created. We're not adjusting it at all, so we just want to return our df as is. Yeah, and so once you type in that return statement, you should not put anything after unless it's in an if statement, but that's way down the line. So in this class, don't put anything after a return statement. A return statement should be the very last line. Do you have any other questions? All right. I'll give a couple more minutes. I'm thinking like I'll go at 8:53, so 5 more minutes. I will go ahead and end it. Unless we get more questions in, and then I'll keep going. But if there's no more questions at 8:53, I'm gonna go ahead and end it, and we can get this live uploaded. Yeah, good luck on your exams, guys. Hoping to get this uploaded right after. All right, I'm gonna say about 1 more minute on the questions. If anything, if nothing else, we'll end it soon. But YouTube video should be uploaded shortly after. All right, last call for questions. If nothing, I'm gonna go ahead and end it. Good luck on your exams. All right, yeah. Good luck on your exams.